Okay, good morning, all of you. We will start our proceeding today. You all should have following things in mind. In all electronic systems, there are two signals which are always omnipresent. One, of course, is the signal which is your input signal. The other is the noise, okay. And it is the signal to noise ratio which decide whether you will get the signal as the output or the noise as the output. Okay. And in particular, low amplitude, low frequency signals, which are more like a hum as we call, is more damaging to the performance because they can be passed in almost all systems. Why did I say so? So when you keep talking very small volume, you think you are actually not creating noise. Actually, it creates more noise than you shout. Okay. This is of course a fun part of it. Let's consider what we were doing last time. We'll still go through few of the slides and start in earnest the course itself. Okay, why I want to show you further, because this is my belief that many of you question us over the years that what's the purpose of all this. Of course, for individual it may be varying differently. For some people you are here because your parents asked you to appear in JE and for good luck you came here. Okay. For some, you are expecting some 4 years to pass with all Moodai, TechFest, BAF, TAF, Modern AM. Okay. Okay. Somehow that 4 years pass, or dual degree student, 5 year unfortunately for them. Okay. So they are just waiting for that time period to be over. If it becomes T is equal to N, immediately they will be very happy. Okay. But there may be 10%, maybe little more, I hope so, who are really interested in what we are teaching. So this course essentially is addressing more to those people who still believe that engineering is interesting and also useful in your career. Okay. If you can increase this number to 90% someday, I think it will be great success for you as well as for me. Okay. Let's start. Analog design needs to consider handling of positive and negative. Last time we said, so we just repeat from there. In case of analog, and I will show you later, biasing is very important. Linearity is essential. That's one problem I'll solve today, or one expressions I'll derive for you. We just now said noise. Since both signal and noise will go through a system, and if your noise is higher, the system does not tolerate it, and then it will pass more noise than the signal. Okay. We also want lower drifts. The word drift is something you are supposed to go on a particular course and you move from the course, is called drift. So let's say power supply voltage has to be 1.5 volts, and if it drifts to 1.4 or 1.6, you may have much more problem at your hand when you saw the circuit performance. Similarly, there are many other parameters can drift. Temperature, for example, 25 degrees what we assume in all, 27 degree we assume 300 degree Kelvin, but in real life when circuits start functioning, there is a heat dissipation in device everywhere, and the board itself will get heated, and the temperature may rise to as much as 35 to 40 degrees, or may in worst case 100 degrees. Okay. So the performance of the circuit has very strong dependence on environment around, and that's called drift problems. Okay. Of course, in many cases there are two kinds of problems one get. One is called systematic. That is, we can predict if this happens, this is going to, so we a priori we know this is going, so we take care. Okay, this is going to happen ahead like this, so okay, I'll take care initially itself. So when it starts, I'll take care. But there is something which is non-systematic, and they are random. If they are random, what can you do? It happens. Okay, and it can happen any instant of time. Okay, so as I said, drift is very important. Both systematic and random errors are very crucial for our designs. In this course, I should not keep saying word design, because I teach a course on analog VLSI design, so I keep that word in my mind. In this course, we are really not going to design things. We are actually going to do analysis, how to design, and not really design. Future, in case you happen to come for master course here or elsewhere, you can take that optional course, VLSI analog, and there we will actually design that how a chip is made and what sizing and how we do that. Okay. But here I think we are doing more analysis. The problem with most silicon chips are that in digital circuit what we do is, let's say I want to make a microprocessor. So what I do is, most companies may have, or at least I may actually have blocks which are pre-designed, prefabricated, pre-tested, memory blocks, register blocks, ALU blocks. These are called standard cells. The new name for all this is IPs, intellectual property. So each can be designed and hold, and no, we won't tell you, you pay me, I'll give you, kind of thing. Okay. So these IPs are not available in analog, because analog is so much varying things. For you will have to create huge number of IPs, millions of them, just to keep, and maybe one out of that will be used. Okay. So it is impossible to actually create IPs in analogs. So every chip or every system has to be designed. Okay, and that's why there is nothing shortcuts in analog, and that's why you have to learn analog seriously, because every case is different from the last one. Then there is a problem in all digital people are looking for 0.8 volt power supply, battery 1.1 volt, say people want to reduce power, mobile, there is a 1.1 volt battery, now they want to reduce to 0.8, maybe 0.6 later, because power dissipation is very crucial for us. So what we are saying that if you do good for digital, which is very good, if you digital may still work on 0.6 or 0.8, but that's against the whole grain of goodness for analog. But since you will always, as I said you earlier, analog will be part of digital, you will work on a bad tools and say, oh, design a great car, but tools are age old, ambassador car ka sab tooling hai mere paas, but you want a Toyota Corolla to come out. So it's very difficult, but that's what the whole challenge is about. Therefore, analog circuits, though we want, but not very low power, but there is an effort, and that's the challenge, that how do you reduce the power even in analog, which is otherwise very difficult to get a good performance. Okay. So these are the issues when we design a chip, though these are not relevant for circuit analysis, but just to give you where we are. So that's the aim we are looking at. Okay, I think maybe my English is not correct in that. What I say is that it should be able to reject much of the noise, okay, so that the signal gets amplified, okay, but noise does not as much. Okay. We'll give you some example, that if I want to have a 2-stage amplifier or 3-stage amplifier, and if I pass through this, the device itself will add to a noise, it's from its own. There is an input noise going on. Now these two noises are now input to the next amplifier. Okay. So it should be tolerant, less tolerant, because it should stop that noise to go ahead. This is what I meant. If I am not clear in that, that's what. Is that clear? So I repeat, the 3 parameters in our analogs are GM, which is transconductance, output resistance, which is very important for us, and the noise, which we, as I say, we define as input referred. This is a very interesting word, input referred. Noise is seen at the output, is that clear? And we say no, but you must specify at the input, okay, what is possible. So there is something word will change from output to input, and we'll say it's input referred. And then finally and the most important parameter in our design or in our circuits is the bandwidth. How much frequency response, that is, let's say I have an amplifier and I want to design an amplifier which will amplify the signal even if the signal frequency goes to say gigahertz. Okay. But this statement is very cheap or simple. Oh, what's big about having an amplifier which can amplify up to a gigahertz? No, most amplifiers will not go beyond few hundreds of megahertz. Okay. There a lot of effort has to be done if I had to amplify at gigahertz. Okay. So this is called frequency response. Okay. And associated, which I didn't say it very specifically, and last time I did say something about it, there is a gain bandwidth as the product which is relevant to us. So if we increase bandwidth, yeah, your gain will go down. So at gigahertz, you may have a unity gain, one gain, that means no gain kind of, or even less than 1. Okay. So not the only solution, because gain has to be remainder something. I want gain of 20, 100, 200, and that gain I must attain. Okay. Otherwise, why amplify? If the gain is not there, this is in life as well. If I put some 2 hours here, I must get a good grade, some output has to be good. Okay. So this also is an issue which is interrelated. So GM has something to do with bandwidth, GM has something to do with the gain. So we must now look at, if I increase GM, what will happen? But if I increase GM, what else will happen which may not allow me to increase the bandwidth or vice versa? That's the crucial analysis we like to do. There are different kinds of noises in the system. One is called thermal noise, another is called 1/f noise. We may not look into details, but just to give a figure, which I don't know whether you can see from here. This is log noise plotted. This is called noise voltage versus frequency. Do you see here somewhere? So initially at low frequencies 1/f noise dominant. Is that clear to you? The figure 1/f noise, and as the frequency increases, it is the thermal noise which takes over. Thermal noise is essentially because of random motion of electrons and other things in the atom, okay, atomic system. So yeah, there is a possibility that some may dominate somewhere, some may. So this FC cutoff may be higher or lower in different devices, different systems. So there is an issue how to control noise, okay. And all analog circuits are worried about this noise, okay. At the end of the day, of course, don't just forget that it is the transconductance which, if you change, will correspondingly change the noise itself, because the expression shows noise square is proportional to GM square. Is that clear now? So if I increase GM for gain and bandwidth some way, my noise is also increasing. Is that issue now clear, that my noise is what I am worried about, okay? As I said, this may not be the major issue for you this course, but just to get an idea that we are worried about noise in all our designs, it has to be clear. This is the word called input referred noise. Vn In square, noise is always expressed as squares, okay, square voltage, because it's somewhere related to power and therefore it's always expressed in voltages. So Vn In square is equal to Vn out square divided by gain square. This is called input referred noise. The reason why we always refer, if you see the expression, you need not know anything. These are all controllable input parameters, and therefore what is the noise essentially will be decided from the transistors and the inputs what you are connecting to. And therefore we always refer noises to the input side by dividing this kind of AV square terms. Okay, just to for design something, we need to work on higher VDD if possible, okay, or what we call bias current should be stabilized. We should also look for, of course the words are, will come back, these are very important words in our analog. PM, what does it PM mean? So PM is called phase margins, okay. So in analog circuit, you can think of phase margin, not a great thing. If you have a signal V is equal to V0 or VA e to the power something, or sin omega t plus theta or plus phi or whatever it is, and if the signal goes through the system, this phi changes to something else, so let us say phi 2, then the margin on phase margin is phi 2 minus phi 1, because the phase has changed now. Is that clear? It's called phase margin. So it's very important for us, because phase margin means something has now changed, not only in the frequency but also in the phase shifts have come, okay, and therefore very crucial in our designs, okay. And they are somewhere related to what we call, and we'll look into these transfer functions. You have not done control course so far, I think so, okay. So maybe I'll introduce to you what is pole and zero. If you have done that course, then I would say pole zero aapne padha hai. So this pole zero, we'll come to expressions and you'll know what I'm talking. They may decide whether system will remain stable. So what do you mean by stable? That if I change the frequency or signal strength, the gain should be proportional. Otherwise, if it changes, then I have worries, okay, and that is called stability of the system. In simple term, one may say, I am designing an amplifier, and if it starts oscillating, that means it becomes an oscillator. It's an unstable system. And this is very simple. You can see from your future when we do, that when I design a good oscillator, it actually damps down and becomes some kind of a damping system. It gives you gain and reduce gains to 0 also. Okay. So when you are trying to get a good oscillator that self-sustained, it doesn't sustain. When I am making an amplifier, it doesn't start oscillating. So I want a constant gain, constant signal, and it's changing now. Okay. So that is a design issue. That when I am designing an amplifier, it should not oscillate, and when I am designing an oscillator, it should not damp. Okay. It should not amplify huge and then damp down. Okay. So these are the two complementary or contradictory terms, which is word goes into word stability. Okay. If it's an amplifier, it should remain amplifier. If it is an oscillator, it should remain oscillator. To do this, we say constant GM kind of circuits is better. There are many methods, we will see if time permitting. Then the other issues are offsets, as I already said, the drifts can occur and how to take care of offsets. Okay. The another issue which I thought you should know, which may not be directly related to our course, but for this lecture I may tell you, there is another analog or the analog cum digital system which is becoming most important as far as the money part in the silicon industry is concerned, which is called RF signals. Why it is called money spinner? Because all of you, barring exception, may be holding a mobile, maybe holding more than one mobile. If I give you 2G, now you want 3G. When we 3G networking start, you'll have 4G. Okay. You want everything on your mobile now. Mobile works at different ways. One is called GSM, the other is CDMA. We'll see that in your communication courses later. So either of this system which you are doing, you have a frequency ranges which is around 890 megahertz and above to few gigahertz. These ranges are called radio frequencies, and since signals, your voice is still analog, much of the inputs you will create are analog. These chips are called, or systems are called, mixed signal. There will be analog blocks and there will be digital blocks. So the RF which we are now creating, which is what we are really looking for nowadays, this is something like a typical mobile system. You can have a look at it. Okay, this is my antenna. This upper part is receiver, the lower part is transmitter. Okay. So we start with first part, which you see here is a low noise amplifier. This is analog, low noise amplifier. Why it is low noise? Because the signal which we received from antenna is very weak. Last time I said the strength depends on how far you are away from the tower. Okay. And many times it's called fade out, you will not even have the signal. Okay. This is why you need to boost. That is the first amplifier which we put is amplifier, low noise amplifier. The interest part in this is because it's an amplifier, it will have a bandwidth issues, which we'll see later. There will be a filter has to be created which will reject the frequencies which are not required from the signal. This is called image reject filters. This is also analog block. You may need another amplification at the after rejection of those frequencies, because initial gains will be smaller but the next gains will be higher. Okay. And these programmable gain means their gains can be modified. Okay. Then we put another image reject filter because you have a bandwidth issue created in LNA. And then we go to what we call mixers, which are partially analog, partially digital. Okay. And then we put a filter, then you have another IF amplifier. This is called image. We have created intermediate frequencies after mixer. Let's say we have gigahertz, we may go to few megahertz, hundreds of megahertz, 200s of megahertz. And we may, sometimes they may have more than one mixer to get a lower frequencies, which is called baseband, okay, 20 megahertz or something like that. Then you may have, this is what I have shown you here, this is another mixer, another filter and your basebands. This is called receiver part. Okay. Beyond this baseband, once I receive, I will convert to digital, and further processing, everything will be on DSP. Okay. And at the end, if you really want to see some displays or something, you may convert that digital data output to analog. Okay. We need to. So two more blocks which I have not shown is A to D converters, and finally D2A converters, but basic processing major will be done in digital. So a transceiver, this is called transceiver. Why? Transceiver is why? Transmitter and receiver together. If you are transmitting, your basebands are here. This is called orthogonal system shown here, baseband 1 and baseband Q. Okay. Two mixers, then you do a adder, which is also analog adder, filter, IF control, single sideband mixer. These are two major amplifiers, which are again power amplifiers and a buffer, which are essentially analog blocks. The power amplifier must have sufficient power so that from the antenna I can transmit for a longer length. Okay. So this is a typical cellophone structure. Is that clear? We may be not interested beyond baseband in this course because we are not looking for digital part. We are looking only for analog part. So one can see all that time what I am talking about in analog. I am looking for amplifier, mixers may be one. For mixer, you actually require a frequency source, which is called written frequency synthesizer, or also called voltage controlled oscillators. Now this VCO is an analog block, okay, which is given to a mixer. So you have how much, what you are going to do actually in analog? An amplifier, different kinds, different bandwidths, different noises. You need oscillators, okay, for different frequencies. Synthesize means different frequencies can be created. Okay. You need filters, okay, low pass, high pass, band reject, all kinds of filters. Okay. These are essential blocks in analog. No more, no less. What is ISDN? Anyone heard? Okay. S stand for what? D stand for. D is of course digital. N is network. Okay. Integrated Services Digital Network is ISDN, which is our BSNL or MTNL, allows you to have all four, that is data transmission, video transmission, computer connection and TV, all can be fax, all can be, or even earlier telex as we used to call, all services can be given on a single line by switches. It's called ISDN. This is a network kind of circuits which ISDN will provide for you. So again you can see there will be D2A converters, pulse generator, filters, line drivers, balancers, pre-filters and tone detectors. All these are basically analog blocks, partly converted from D2A, digital to analog, and now you do processing on analog part. Okay. So this is very, is it ISDN is replaced already by what? Cable modem. Cable itself can do all the jobs. Wireless can do all the job. LANs are come, WLANs, okay. Wi-Fi, WiMAX. But what is the problem with what was the good thing in ISDN? Because it was on your telephone line, which in old days, you will not believe it, your parents may tell, to get a telephone in Mumbai as late as 80s was a nightmare. Okay. To register, and after 8 months, 1 year, 2 years, depends on if you know someone or you don't, you may get your line. So getting an ISDN was for an institute was an achievement. In 80s when IIT Bombay got ISDN, a director was thanked. That is what essentially. Now we have changed so much, you don't realize, but there was a time when we actually worked on such poor systems. Okay. These are essentially circuits which are called frequency modulated transmitters and receivers, and you can see there are, this is shown intentionally bipolar because these are old circuits. You require inductances, capacitances, resistances, transistors, and different transistor sizes. All this, and of course you can have a loudspeaker, you can have microphone, and this was our old system. But basic even now has not changed, because you cannot change the basic operation of an amplifier or an anything. So even if we have done much more work to simplify it or reduce the components, the basic idea of analog circuit design is still same as 50 years ago we were doing this. Okay. Like mobile, WLAN, GPS are examples of RF. The trade-off in why RF design I am showing you for your sake In the case of digital, I did not show you very much, but I showed you that there is a triangle of design, or what we call trade-offs. What are the three things last time I showed you? I said, I don't know whether I have shown that figure, if not I will again show you. This is, let's say, power, this is speed, this is how we call area of the chip, okay, or transistor area. So if I want to reduce power, then I will reduce speed, but I may actually increase, or if I want same speed, then I may increase the area. So triangle has to be pulled up or pulled down, but the net area will remain same in the technology. So you cannot achieve all goodness because of the triangle limitation. But if you see RF, this is the problem. How many things we controlled there? 3. And how many now I am controlling? Almost hexagons, 6 of them. Maybe a better figure can be here. You have a linearity, you have power supply value, you have gain, you have frequency, that is the bandwidth, you have power, and you have noise. And now you control one, the other is going to be affected. So when I start designing an analog block, I am worried about particular RF. They'll say, okay, this is 0.8 volt, mobile cannot get more than that supply. Oh, that means now I have reduced this, I don't have enough currents. Oh, so how much gain I can get? If I increase gain by size, I may lower in frequency because capacitance has increased. No, I want, okay, then I must push power, that means I must increase currents. If I increase current, I will increase noise. So I have to keep worrying now that how do I optimize most of it, okay. But you cannot achieve all of it. Is that clear to you? Why these limits have been shown? That don't tell me that 0 volt, infinite gain, infinite frequency, 100% linear, 0 noise, 0 power is achievable. This is not done. Okay. If you want something from me, you must give me something. Okay. That's the world. That's how world works. Is haath le, us haath de. Okay. System is similar. So in our designs, that's what the designer's job is, to optimize the best of it and say, okay, this is not achievable, but this I can do. So you cannot have everything, but okay, if this is your more important parameters, okay, I'll control them, but they are at the cost of other 3 or 4. Okay. So someone has to optimize this design. That is why engineers are required. Is that clear? What is the issue I am raising all this? I am trying to tell you that automation is always possible in digital many ways because there are fewer parameters to control. In analog RF designs, there are too many to control, and manual intervention is essential because every person will come with some other requirement and it's, oh my gosh, now how do I achieve this? So your design approach or your analysis approach should be very good because you have to meet someone's specs which will be different from your next circuit. That is why the analog circuit essentially is slightly difficult, some may say, but more interesting because otherwise there is no, this is required. We keep saying digital people that you don't need this, you do it automation, you give something and it will give you finally. At the end of the day, computer scientists make as good a chip as electrical engineers. Okay. Why? Because there is so much software available. You can download many things and start designing, and chip may work as well. Okay. Because someone has already standardized that and can be used there. Analog, there is nothing, something. Every minute I need myself to see what's going on. Okay. Therefore, please remember that why analog RF designs are important or difficult is because of its requirements. The major problem which I said you is in wireless applications, which are the major applications. Why I say major? आप सब लोग जितने मोबाइल यूज करेंगे उतना VLSI और सिलिकॉन कम्युनिटी आपको थैंक देगी. पेरेंट्स न दें, they may not like that, but as a VLSI engineer say, oh thank God, use 2 of them, 2 iPod भी करो, iPad भी करो, ये भी करो, उतना पैसा. So industry is actually working on wireless systems now, okay, which is more money spinner than anything. So we have the other systems like Bluetooth, WLAN, set-top box. You must have seen nowadays almost everyone you have direct TV home, DTH. This is essentially you have a box there which actually picks up a frequency of your choice and does the set-top box. Set-top box. Okay. Why it was called top? It is put on something. Set-top box. Okay. Then there is intermediate frequency and baseband part of radios. There is a radio which has come which is called software radio. Think of it what I said, okay. Software radio. Okay. It's something different, nothing to do with radio per se, that is the radio receiver, but the word is software radio. Okay. There are many challenges in mixed signal, and why CMOS? Why did I say last time? Because that's the technology digital people will force on you. Whether I like or I don't like is not my choice of analog. Analog say, "Arey baba, bipolar do," but that doesn't work. They say this is the technology. Nowadays, what is the kind of technology we are working on CMOS for digital chips? 28 nanometer. That is the channel length is of the order of 28 nanometers. I started working in 70s when we worked on 50 micron channel length device. Okay. In my 35-40 years of time, now the devices have reached channel lengths of 28 nanometers, 289 angstroms, okay. And sooner we may actually reach 11 nanometers in few years. First we go for 16 and then maybe we 22, 16 and finally to 11, and if things go all well, 0. Okay. Okay. So that's the technology. But analog people will see later, longer the channel length, he is very happy. He said thanks, okay. My gains are good, my bandwidths are good, okay. But digital say, oh, but 28 nanometers. That's what Intel has come with all new microprocessors at 28 nanometers. So the problem, you got the point, the problem is bad tools for us, good for digital, but then you work for those for this technology. That's why it's called mixed signal design. It's tougher than pure analog. Why? Because pure analog, I may use bipolar. Why use MOS? I have better choice. But if I had to work in the money making chips, which is wireless as of now, for example, then I have to go for what digital people will say, and that's what we are doing right now. If we shrink the device, there are many other problems like short channel effects, there is a problem of breakdown problems, there is a non-linearity problems, there is a coupled noise problems, there is a huge flicker noise adding now, okay. Okay, so point I am trying to say that there is, what is this NQS in device course? Anytime you heard the word? In the devices, if I apply something, the response time, for example, if I change bias, the device doesn't respond instantaneously, you just change the bias externally, internally it takes time, there is some issues going on, okay. But in system, what do you want? We want a steady state. So we may not get a real steady state, we get a steady state which we call quasi steady state. But in very low channel circuits or low channel devices, this even quasi steady state is not possible, non-steady quasi static. Now how to model something like this which is non-quasi static? This is a major issue in modeling in the case of sub 30 nanometer devices. To get quasi we modeled, we say okay थोड़े देर के लिए तो steady state है मान लेते हैं, अब ये वो भी नहीं है, तो what do you do? Okay, that's the issue. At RF frequencies, steady state is not possible. All over, do you solve the continuity equation? You say steady state. इधर से आया उधर से निकला, steady. Now, if I don't apply continuity equation for device, how do I get the relationship between currents and the fields? Poisson's equation cannot be, because I can't get now doping exactly, so I cannot put in field equation. So quasi steady state was assumed in most devices, but when I go to a lower channel devices, this is modeling. So this course has nothing to do with it. I just want to tell you why we are worried, because they are telling, means I am now talking myself analog man, when I sit on digital I tell those otherwise people. So digital people forcing us to think much more now, because they are moving in one direction which we don't want to go, but we will have to go, kind of thing. This is what I said, digital design is getting so much computer aided design tools, so their designs are not very difficult. Okay. Analog circuit still remains a handcrafted art, and that's what the word I use say every year, it's an art. So it's called art of electronics. Okay. It's not art of designing, it's an art of, it's an artist, it's not even science. So all cannot become a good analog designers. So all cannot become artists. I may actually paint by putting some brush here there, but it doesn't make sense. But normally, usually what we understand painting. So it's a crafted art. How good you are analog designer is individual, and that much how much depth internally you create for yourself. Larger percent of die area analog, it is much easier if larger area is given, but they will give very small area to us. That's an issue problem. 100% area में 5% analog. अब उसमें सब करो. So that's worrying us in every way. Okay. Then the design time it takes very high because individual blocks have to be designed. So it takes time. Time means what? Money. So many design engineers will be working, so much man years, so much money. So analog designs normally being smaller, even then they take larger design times because they need to meet very stringent specs. Okay, cost of mixed signal chips, analog part costs approximately 2.5 times. That's what they, let's say in a 0.18 micron as did in 0.35, because it does not shrink. As digital everything like scaled they say, 0.5 half kya 0.25, half kya 0.1. Nothing happens in analog like that. Okay, so that cost never reduces, it actually increases if you go further. So it's worrying that analog blocks are costlier than digital blocks as you are shrinking. Okay, because you will require more effort now to design on that. Is that okay? Another problem in mixed signal is, since you have both digital and analog on the same silicon, they are connected internally in the substrate. So what is good may be good, but what is not, it may actually create problem for the other. Okay, particularly digital switches. Do you understand what is digital? 1010. At higher the frequency, it will do even faster. That change will apply to the bias at the substrate. That will become signal to analog as a noise. Okay, so this inbuilt noise creation from the digital is constantly through substrate going to analog, and he is worried. That's why I say analog, particularly in the present era, is becoming difficult. Is this okay? Just more interesting figures. Nothing great now on theory. This is a very standard broadband network. Okay, you start with a packet network infrastructure gateways. Maybe we'll show you. This is your prime access gateway, which is connected to so many applications: camera, pad, iPad. Then this is your mobile. This is your desktop. This is your TV. This is your fax machines and telephones, and this is your laptops. So everything is connectable through a broadband. So then you will see figures. So that is the lifestyle you all want to be. You want to sit in your house, work somewhere else, and you want to do everything almost by click of your tick should happen. Okay, this is possible. Okay, this is possible. That's what you all want, and this may happen soon. And most people are already working on it in many countries. Like for example, in many European countries or in US, even in India now. Your pressure cooker or what is called electric cooker, the person can switch on at a given time and after some time switches off. Washing machine may start after some time and switches off, kind of thing. Sitting at the fag end, you are working, okay. Or let's say your ladies who work also. Nowadays 50% of the VLSI industry is manned by the other sex. Very good, 50% is a large number. 33% they were asking, now they are already 50%, okay, in most silicon industries. Okay. This is a cable network. What is cable network? All of you, those who doesn't have this Z or big TV DTH home, still may have a cable coming from your cable operator, okay, which is 4 gigahertz cable line, which is hanging around the road, hanging around everywhere, finally reaching your home. Even that can be connected. Through that, you can actually do most of the connections now. Okay. You look at the video where both analog digitals are required, a camera, cellular, video DMA. What is DMA? Network camera, IP video. DVDs, D1 DMAs, IPSTVs, media, video surveillance, video on demand, broadcasting, everything right now what you see as both analog and digital components. This is the fiber links. Okay. We are looking for bandwidths of the typically around 100 gigabits per second, okay, which is shown at 64 OC48 circuits, and we may go for multi-fiber, multi-mode, and may increase further the transmissions. Our ultimate aim that repeater should not go before 100 kilometers is what we are looking for. Right now, every 3.5 kilometers there is a repeater for optical fiber. Okay. Some new fiber lines have up to 10 kilometers, but most have 3.5 kilometers. Earlier it used to be 1 kilometer. What's the problem? If it breaks, you'll have to remove that link, splice it, re-weld it, put another transmit receive there. Okay. So that's the issue. Now we are increasing that to 10 kilometers. That is what we are looking for now. Okay. Yeah, broadband is going to grow, fueled by consumer demand. Broadband access is evolving high speeds. Because you want an internet, very high speed internet, that's why broadband is being pushed very heavily. Okay, we'll move. This is something else. There are three problems in integrated circuits. The first problem is power. We want to reduce it. The second is interconnect. How much length I said in Pentium 4, first Pentium 1 kilometers, and the present Pentium or Xeon which has come has 3.6 kilometer length of interconnects. So on a smaller chip of 2 centimeter by 2 centimeter. Do you get the point? It's the perimeter. How many times you go like this? That's the length. The length of the chip is no more than 2 centimeters. Okay. So don't think that 2 centimeter में kilometer कैसे. Okay. So that's our major worry, because if something is going that far, my signal will attenuate by the time it reaches few meters. Okay. Because so much capacitance on the line, it will just RC time constant खत्म. तो उसको boost करना पड़ेगा. Boost किया तो phase margin आएगा. फेज मार्जिन आएगा तो एक क्लॉक या एक सिग्नल दूसरे क्लॉक में फेज में नहीं है, उनको फेजर लगाना पड़ेगा. So there are issues which are called interconnect issues. Then of course complexity, number of devices. Transistors are reaching millions. 42 million transistors in Pentium 4. Pentium 4 first one, Pentium 1. Now we are going for 800 million transistors. Pentium normally 4, which is 142 million. The present circuits can go up to 850 million transistors. Okay. Is that clear? So that's the complexity we are handling. Power crisis. The major worry in power has come because of the devices becoming smaller. There is something what we call leakage problems. Now in earlier times, this word never came to our mind. Okay, off current. Off current means when for a digital, for example, when the input is 0 or lower level, no current passes in the circuit, we say. That's what is switched off, we say. But we assumed that time that the on current, when it is turned on, is much larger compared to off currents. Okay. 1 milliamp, and this may be nanoamp. Okay. But if that 1 milliamp has become now hundreds of or tens of microamps, and this has increased from few nanoamps to tens of nano, we are closer by. Okay. Even if 50% of the circuit is off, and there are 100 million transistors, let's say 50 million inverters on that, half of them are off. 25 million into this off current is not a small power, which you thought earlier 0. Okay. Since the complexity has increased, the off current itself has increased, and on current hasn't increased very much. In fact, it has decreased because of power requirement. So now this is a major issue. Circuits start failing because of the off current. Okay. The joke is, if you work on 28 nanometers, 66% of the power is off power, and 33% or 34% is on power. That means if you keep your mobile on, it will consume 34% of the power. If you put it in standby, it will actually drain your battery more. That is why I do not discourage you constantly talking on mobile, because at least net energy of the world is saved because battery is not getting drained. Okay, is that clear? Okay. Okay. As I say, number of interconnects are increasing enormously. Okay. There is a noise issue. There is another issue has come. Two interconnect lines. Interconnect is a metal layer. Metal sitting on some insulator. That's how interconnect runs. But this is like an RC circuit, which means like a transmission line. Okay. Now when the two transmission line come closer, they have a capacitance in between as shown here. These are two metal lines, three metal lines. As they come closer, epsilon A by D is smaller, they couple. So signal passing in one line may actually get coupled to either side. Okay, this is called crosstalk, as I said last time. Okay. So if you shrink, reduce everything closer, this will kill you. Okay, so interconnect issues are very interesting because they pick up too much noise in all this work. Okay. And finally, as I said, the number of transistors are increasing, number of kinds of circuits we are increasing. The board has becoming very big, and to maintain their connectivity proper is becoming a very important. To design such a large system is very difficult. So we design blocks and try to put on a one common platform, which is called system on chip. Okay. This is the current trend, system on chip. Okay, SoC. There is also another game being tried by Japan and some other company, which is called system inside package, SIP. Okay. That means you have number of chips put inside one package. It's called system in package. Okay. This particular has 28 chips. Sony camcorder has this chip, which has a DSP, memory, many things. There are 4 layers, 7 chips on per layer, 28 chips package, one single package. Okay. This is called system in package or system inside a package. Whereas the other one is like which we call system on chip or SoC, where each block is given an area where they are mounted on a single wafer or single area. It's called system on chip. Okay. These are possible mechanisms in which we may work future. It may actually get analog, it may get digital, it may get MEMS, it may get all kinds of circuits can be separately connected properly, so that you may design a large systems. This is what at the end we are looking for your times. This is 2014. We are going to work on 3.6G. Will require for strong control on VTH. We are working for 35 nanometer. Already we have crossed. Okay, forget that number now. 17 gigahertz clock we want to run. How much clock we are running in microprocessor which you use PC? 3.4 gigahertz. We are looking for 17 gigahertz chips now. Okay, this will be the greatest thing to happen soon. Okay, this is what the world is looking into. 10-meter wide road. Designing a map of 10-meter wide road for a world atlas is what essentially VLSI design is. Okay. I'll just give you the last few slides. I don't know, because many of you were not even born, okay, in 70s. There used to be a famous in LA there used to be a famous serial based on some secret agent called Dick Tracy. Okay. This name was Columbus actually, and he used to have, of course, if you are even at your age, you could have seen some of the 007 Bond films. No, he makes a lot of tricks on those. They were only for film those days. But all that what was they were showing then, like he has a camera, he has a music, everything on his watch. In 1976 serial they showed this. Okay, Dick Tracy. In 1998 or 97, Sony came out with a watch which does not only what Dick Tracy was showing in 70s, but does much more than what Dick Tracy could do. Okay, that is the progress integrated circuits have done. Okay. Similar thing came from Samsung, which has a similar watch, which has a camera, which has a mobile which has, of course watch is also there, okay. Many other things. ये क्यों joke किया? Of course we are also part. Many times we are invited for tea in the evening by some family, and other than tea everything is served, So इसलिए बोला watch भी है उस पर. For silicon people, this is very important. These are actually a silicon wafer with this, each is a chip. Now it is at the horizon, okay. Now if this gentleman is a optimist, he will say like a sun, this is coming out, still the full blown has to come, okay. But let's not put names someone, maybe XY of you are pessimist, oh it's now shrinking, it's go down, it will now finish it off, okay. Depends on what you are and what you want to think. Silicon is going to stand till 1950, come what may, okay. 1950. Your half the career will be made on that if you join silicon. This is what all of us wish. Jairam Ramesh wants us to do like this. By the way, Jairam Ramesh is distinguished alumni of this institute, okay, from the civil engineering department. I don't know how civil is connected to environment, but maybe. Public health is one of the part of civil. This is called nomadic society. Nomads move from one place to the other and they don't stick to a place, okay. So if you, in a modern era this is possible, you can have all kinds of a small laptop or some kind of a which has every control what you want. You can live in a jungle or you can live anywhere. Your office may be far away in a distant city of 3000 miles or whatever distance you think, from good environment around nature, everything, and you are still working for that company or your home or anything. This is what is possible in a very near future. Okay. Finally, before we quit on this, this is for those who don't want to remain engineers. This is my advice. Executives might make the final decisions. All managers do that, okay, about what would be produced. But engineers would provide most of the ideas for new products. Managers don't get ideas, they only manage, okay. But engineers get ideas, okay. After all, engineers were the people who really knew the state of the art and who were therefore best equipped for prophecy changes in this technology. So if you really want to remain in best of your minds, continue to remain engineers. One of my 84 graduate, then of course did masters also in computer science, not with our department, Mahesh Mendare, Dr. Mahesh Mendare. He is the director of Texas Instrument Bangalore, and he is the only Texas Instrument fellow in whole Asia. TI allows any academic excellence which has contributed to TI's progress a honor which is academic honor called fellow. Okay. So he is the only Asian fellow. TI has a work in Japan, Korea, China, Singapore, even in country like Sri Lanka they have small base, Iran, Iraq, of course now they are closed most of it, okay, Turkey. Of course Turkey may not like to be called Asian, but Turkey, all these countries, and Russia. So all these countries, only fellow is my student management. Why? Because he chose not to become manager, but continue to work for the progress of science in TI. He has some 65 patents, and 3 of his patents have got the best awards. Okay. And therefore he is called director of technology, and he doesn't report to the MD of the company. He starts his own projects, and of course approvals are required in Dallas, but he doesn't have to report to anyone. Okay. That's his strength. So if you really want to remain in engineering disciplines, you have a good example from IITB. You can still reach the best and still remain as active in academics as you wish to be. Many of the PPT shown to you are taken from Sony Corporation's PPT given to me by Sony's vice president. many of there is a standard book by Professor Razavi on analog circuit. There is a EDA company called Cadence, so some of the slides have been done. Actually in India, there is not a single VLSI company which does not have IITB students, both graduates, dual degree as well as postgraduates. And since I being here too long, most of them by force studied like you have been forced to study with me. They had to study, go through me, and if they are doing analog VLSI or digital VLSI, they must have done my course. So I say I control Bangalore and Hyderabad. Okay. So most companies, if you see, these students come here, sometimes give lectures, sometimes give, so this is latest. That's why I get the latest PPTs, because of courtesies of people like you, who some of you still want to remember me. Okay. There are many websites on VLSI available on net. Okay. There is a book on digital circuit by Rebe, which is very good book for digital. So that's one from there. Of course, and finally, thank you for this. So this is, I hope that we'll just introduce few things and then stop. By now you must have understood why I showed you all this for 2 days, and I wanted to make a distinction to you that all other jobs are as good. At the end of the day you want to be happy, maybe good, prosperous happiness, okay, and everything. You want 3 cars, 4 cars, everything is fine, but the job satisfaction is the first thing you must look for, because at the end of the day if you are very unhappy on your job, nothing will be as good as you think. You may provide everything to your family, but you still will not be happy. So at the end of the day, if you are happy with the banking, doling money here, there, writing a report, fair enough, nothing absurd or nothing wrong, but all need not do that job. Okay, some should do engineering and be happy if you are learned, and if you want to do good and be happy, learn what engineering is all about. That's why we are actually showing you what is in future, what was in past, and what's going on. Okay, so that you can correlate yourself where you can probably fit, maybe unfit. As I said, we will for next 10 minutes we'll quickly go through some of the issues of analog again. Analog circuits can be implemented in 2 technologies, as I said. One of course is bipolar, the other is MOS. Okay. As I said earlier also, bipolar technologies are not out. There are many chips still in bipolar available in market, and therefore one cannot say one should not learn. Secondly, why I still want to do bipolars, because it's called pedagogy. That's how we started. मेरे समय में MOSFET नहीं था. So I learned vacuum tubes. I didn't have any transistors. You probably don't know what is vacuum tube. Maybe you look at the web. Huge 6 to 8 inch kind of glass tubes inside, grid, plate, cathode, like at CRT. We used to have tubes, 300 volt supply, DC. Okay. That's how we learned electronics. Things have changed. Okay. So bipolar is still not out. 741, many of the op-amps are still on bipolars. However, major technology, as I said, is MOS. So we will concentrate also on MOS designs, because that is what is now going on. Okay. Both certainly have some advantages and some disadvantages, and depends on the system requirement. One may choose to go on fully bipolar or fully MOS. Because the most systems in marketed are mixed signal, they are mostly on MOS. So we will like to see what happens if analog is put on a digital technology. Okay. That is why the worries are. Okay. Otherwise, I don't see any worry. Okay. Let's look. You have done last semester a course. If not, please revise your course, because I will not teach devices course in analog. Okay. The basic transistor shown here is an NPN transistor, can be a PNP as well. The symbol is arrow coming out is NPN, arrow going at the emitter is PNP. Typical NPN transistor is shown here. This is emitter which is heavily doped N plus, sometimes N plus plus. Then small base width, shallow doped or low doped P region, which is the base connected, and a little lesser doped than N plus is the collector region, and this is the symbol of currents we have shown. IB enters, I enters, so is IC enters. Okay. This is the symbol. In real life, these symbols have no meaning. Why? Because current can start, or the circuit wise, the current can be shown only starting from positive terminal of the battery and should end at the negative terminal. That's what the circuit is worried about. So irrespective what happens inside or whatever you may say for the device, actually currents will start from power supply and will go to the ground. That's the way it will happen. Now you may have to say, no, but you are showing this symbol and the actual current is this. Yeah, that may be electron current going down, but the actual current is going up. Is that clear? So symbol in devices and symbol in circuit may sometimes vary because of the carrier which you are going to use in different devices. This is a symbolization, but don't worry, this is for device. In real life, please remember, circuit always will start current from positive terminal of the battery and will end at the negative to form a circuit. Unless it returns, no circuit, and unless circuit is formed, no analysis, no current. Okay. So there is a universal thinking in bipolar, as you must have learned, that the emitter current is always sum of base current and the collector current. Essentially what we say, when the emitter injects electrons, part of the electrons are recombining in base, okay, constituting the base current, and the rest will go to the collector. Okay. However, in this there are some leakage currents we are not added, but that may happen because there are two diodes, they may cancel. So basic idea in case of circuit, please take it, these are circuit. We may, in reality devices, small changes may occur, but in circuits, emitter current is always sum of base current plus collector current. This is our universal theory. Okay. We also know the collector current, as I just now said, not all electrons starting from emitter reach collector. There is a transport essentially because of recombination, because of the efficiency of this emitter junction and the base transport it does. There is a term which is called alpha T, is base transport factor, and emitter cannot have 100% efficiency, so it has emitter efficiency gamma, and the product is called alpha. Okay. And IC is equal to alpha times I. Please take it, these are circuit equations. Some modifications will be done in real life in case we need leakage currents to be added, but normally these will be followed in most circuit cases. We also know that the collector current divided by base emitter current is alpha, but collector current from this equation now, use I is equal to IB plus IC in this equation, and then you will get IC by IB is equal to beta, which essentially from this term will come alpha upon 1 minus alpha, and beta is essentially called common emitter forward current gain. Okay, is the major parameter in all our analog circuits. Beta, how much is the beta? Why? Because typically the inputs will be given at the base, and how much beta times it will provide you the collector current. So larger the beta, larger will be the gain, and therefore it's called gain. Okay. Typically gains can be as low as 2, 3, 4 or 5 and can go up to 500 to 600. Okay, this is possibility. Why 500 to 600? You cannot become alpha is equal to 1, beta is infinite actually, but alpha can never become 1 because alpha t cannot there will be time, there is a finite time or recombination time in the base, and there is not all electrons, there will be reverse current also coming from base to the emitter. So gamma can never become 1. Since gamma can never become 1, alpha t can never become 1, alpha can never become 1. So beta cannot be infinite guaranteed, alpha will never become 1. So as high alpha you can get 0.999, that may give you 1000 beta. Okay. Is that correct? So maximum possible alpha you can get in most technology of device may be of that order, which means not more than 600, 500 beta can be achieved. Is that correct? This is technology limits. If you can do better someday, yes, you can improve, but that's very difficult. I am not saying impossible. We also say if you want little more accuracy, IC is not only alpha IE plus some collector leakage current, which is called when the emitter is open, collector is open, whatever is the collector base emitter junction is open, whatever is the collector current you get is called ICO. Okay, and we'll devices you please read. If you have no, if you do, some of you don't know or not understood, you come me separately out. I'll explain the devices much more detail if you wish to. Okay. So right now assume that this is what I can use in most circuits, but if I want little more thinking, I may add a term ICO to that. Okay. ICO of course is decided by ICS, which is reverse saturation current of collector junction, into 1 minus alpha R into alpha R. What is alpha R? Alpha F is, that is collector acting like emitter and emitter acting like a collector, is called reverse operation. So alpha is the reverse operated alpha of that. So IC by IE, opposite way if you do it, it is called alpha R, that is emitter becoming collector and collector becoming emitter. Essentially what saying, in normal operation base emitter junction is forward biased, base collector junction is reverse biased. If you do the contrary, base emitter junction reverse bias and base collector is forward bias, the carriers will come from the other side, okay, and that is called alpha R. So it can be proved by device theory that ICO is reverse saturation current ICS into 1 minus alpha R, and that you can evaluate ICO. By measurement you can do easily, just open that circuit and measure the current in the actual circuit, that is the ICO. Okay. We also have one Kirchhoff law always followed. VCE is, if you see this VCE, and this is your VBE and this is your VBC, you can see from here at between the two nodes you can have only one voltage, between any two nodes you can have only one voltage, between this collector junction and emitter junction if you have a voltage VCE, but if you go through the other side of the loop, you go from emitter to base and base to collector, then the sum total of base emitter voltage plus base collector voltage must be equal to VCE. And actually this is the fun, that the operation of the device which becomes saturated, that both junctions become forward biased and therefore VC goes down, is very interesting. Maybe someday we will explain that. Okay, that is what digital circuit we will want, okay, that VC should go down to 0.1 volt because that is the zero state of the logic. Okay. In analog we will never like to do that, because what did you yesterday, I showed you a figure, I want to be in linear region of V0 Vin characteristics all the time, okay. Therefore I will never like to do to saturation areas, actually I will remain in the linear area all the time if possible. Okay. So this equation is again valid all the time, VC is always equal to VBE plus VBC, okay. This is Kirchhoff law, between two nodes same voltage can occur, okay. Okay, the second third issue which is of relevance in bipolar, there is something what we call large signal model, but what we are interested later is small signal model. But let us see what is large signal. We said this is what we are showing you right now, DC values essentially is called large signal models. Typically a bipolar transistor can be shown as base emitter junction is a diode, base emitter junction is a diode, and base collector junction actually has a collector current which is beta times IB. So it is a current source depending on the base current which is decided by the diode at the base emitter junction. Is that correct? Whatever VB I apply, e to the power q VB by KT is the diode current flowing, NKT if it is different device and different regions, but the diode current is the base current. Is that clear? Is that clear? Diode current is the base current and beta times that base current is collector current. That is our, okay, I must show you IC here. IC is beta times, that is what equations we wrote, that is the representation of what I wrote, I am showing you in this circuit. Now why do I want to always show some numbers as representation? Because at the end of this, when I solve an analog circuit, it is a circuit, there is no device there. I cannot use diode there, is that correct? Because then I have to write exponential terms, this. I cannot solve in a circuit such thing. So what should I want? I want equivalent of that in a circuit. So I say okay, when the diode is on, it is like a battery of VB on, which may be more than 0.6 volt, cutoff is 0.6, maybe 0.7 volt, which will assume. So VB on in all circuits, when it is this, will be assumed 0.7 volts. Okay. If it is less than 0.7, we say it is a going towards off state now. If it is more than 0.7, it will go to saturation. Say 0.75, device may actually saturate. So this 0.7 volt is not exact number. Actually, whatever bias you are, accordingly it will calculate. But for circuit people, 0.705 or 0.699 is no meaning. They say 0.7 is good enough. Is that clear? So something which I am now representing is for circuit analysis. Device people may not say करेगा क्या कर रहे हो ऐसा इतना पढ़ाया और ऐसा बोलते हो. For us, that's good enough. Okay. Similarly, if you are looking for PNP, since it is a opposite polarity device, the diode is shown opposite way, P lower and above. Here P above and lower. Is that clear? So it is just NP and PNP. It represents C. The base current, if you are really looking for, is the saturation current divided by beta into exponential VB by VT. What is VT I wrote? VT is KT by Q. Okay, it's called thermal voltage. Okay, VT is called, but this I will stop writing afterwards, because in VT in the MOS transistor is what? The threshold voltage or turn on voltage. So I should not confuse that VT with this VT. Just now I wrote VT, but later on I may use KT by Q everywhere, so that no misgivings about threshold voltage of MOS transistor and VT here as thermal voltage. So similarly I can say VB on IB, beta times IB. This is for PNP. Is that okay? Simple model. What is missing here? There are many important parameters right now I have not added. For example, there are resistances, capacitances, whatever is going to happen right now I have not shown. This is called simplistic model of a BJT with add-on terms in real life. Oh, ये तो इतना ही दिखा, add something. Now what is the way method? We'll first, many times what did we do? We actually looked at the device and found some numbers and added there. What is the inverse way? We did measurement and this simple theory did not meet. अरे आप क्या ऐड कर दें, अरे यहाँ थोड़ा रेजिस्टेंस डाल देते हैं, वो ड्रॉप दिख जाएगा. So there are two ways of learning any circuit. One is do it and do not find the correct theory, so add theory from your side which get the model, or you create a good model and then verify on there, oh it works, okay, it will. Okay. So when we give a lab, many students ask me कि सर आपने अभी theory तो पढ़ाया नहीं और lab दे दिया. Nothing happens, because you do first and then when you start looking at theory, oh now I understand why it happened, or you can even start thinking earlier. So don't go and tell the lab people, oh, professor has not taught this, how can you give me experiment? No, you do an experiment otherwise, okay, and then learn the theory back, or you learn the theory first and do experiment later. So it depends on individual choice as well, but this is way I look at it. So every time we used to give a lab, people used to say आपने तो अभी खुद ही ने नहीं पढ़ाया. मैंने कहा हाँ पर यहाँ करो आप. So this model which I showed you is called large signal model, 1 minute, and this is called small. We'll come back later next time. This is most important thing which I want to use. This is not for BJT, for every model, but here it is shown for this. We will say the total base current, let's say, is represented by capital I, small b. Is that correct? Total base current is small signal current, which I represent at small ib, okay, plus the DC base current, which is capital I, capital B. So small signal plus DC is equal to the total current. Is that correct? So total current is represented by capital I small b equal to small ib plus capital IB. Is that clear? This is my symbols. So if I write one way or the other, you must understand which terms I am writing. In the case of collector, there is some issue because see, chota or bada is very difficult to draw. Okay, so I made smaller one as a bar to show that. So this is total IC current, which is equal to DC collector current plus AC or small signal current IC. Okay. this is a transfer output characteristic of a transistor. We will come back to it next time. But most interesting part from the circuit, why I showed you this just now before we go ahead, I plotted collector current versus VCB. That is output volt. What is VCB in that figure? If you see my VCB, which is in the common emitter circuit, this is your output voltage VCB. Is that correct? This is your input current. Okay, this is your output current. Let's look at it. This is your IC. This is your VCB. If this I ground, this is my output VC. So that's what I say. Okay. Oh, there I may made a mistake. I should have. I'm sorry. VC. I'm sorry. Okay, I apologize. Okay. So if I plot out, I kept saying it, but I think in writing I made a mistake. So if I plot VC versus IC current, which is the output characteristics of a common emitter transistor, then for different base current, I see different characteristics. As I increase base current, the collector current beta times IB, and in non cases it may not be linearly related. It shows different regions of bipolar operations. However, the issue which I want to show, in real life, if all these characteristics at different IB are extrapolated back, okay, they all meet at a single voltage which is called Early voltage. What is Early voltage in device? If I start increasing VCE, essentially I am increasing VCB. Please tell it VCE is equal to VCB plus VB, I may fix. But as I increase VCB, I increase VCE. Is that correct? So if I increase VCE, as I increase, what will happen to base collector junction? Its depletion layer will start enhancing, depends on the doping on both base and collector. Majority it may deplete first towards collector because it was kept N minus. Okay, so most of the voltage will be sustained in the collector region, but base will also start getting depleted. Is that correct? And some voltage base may get punched, emitter and collector may get shorted through a depletion layer. That is called punch through or called early voltage. Is that correct? At that voltage, at that VCB or VCE, we call the device is punched. Okay, this is very important parameter for us, because if you see this slope, please look at it, this slope. For any current, this voltage, this is very high. Typically, early voltage will be 50 volt and 100 volts. VC will be 5 volt or less. Power supply is at best 5 volt. Typically 3 volt, 2.1 volt, 1.5 volt. So this 50 volt divided by the current is what? Voltage divided by current is what? This slope. Resistance. Which is this characteristics I am drawing? Output. So what resistance I am talking? Output resistance. So if I am given early voltage, I know the output resistance of the transistor immediately. Is that correct? Since I know this, at any given current, this divided by this is my resistance, and they should all show roughly same slopes, same, because they meet at same point, though R0 varies with every base current to some extent, because your slopes are different, okay, but majority at that current wherever you are operating, you will know what is the output resistance of the circuit. So from the circuit point of view, if I am given a early voltage, indirectly I am telling you, whenever you will bias it at a given collector current, I know what is the output resistance I have chosen. Is that clear? That is why I showed you this slide, that many times R0 is not specified, but early voltage is specified, okay, and from there R0 is known to us. Is that clear? That is how we will actually start working later. Thank you for the day.